All right, thank you. All right, so let's go ahead and get started. So today we're going to do transformations of functions. And so we're going to go through each of these. So we're going to do vertical shifts, horizontal shifts, reflections, vertical shrinking and stretching. We're going to do horizontal stretching, then we just put it all together. And you notice your homework's just to put it all together. And then we'll do even and odd real quick. It's just a real quick thing. So let's get started. All right, so let's start with vertical shift. So this is the simplest thing this is the simplest transformation to a graph. So if I take a graph and I take a function and I add c to it, it just moves the graph up c units. And if I minus c, it moves it down c units. Probably on the exam, when I give it to you, just say, I'll give you something and says, how would you transform this graph? Do you move it? There'll be like a little drop down menu, move it up or down x units, and you move left to right x units or whatever. Or I might make a multiple choice. I don't know. I'll mess with it and make sure it's fair for you guys. Okay. So let's start here. So if we have some graph, so let's draw the same graph twice. So let's pretend this is my f of x, and this is my f of x. So if I have the same graph, if I shift it upwards, I'm going to go up by c. In fact, let's just use different colors today. So here I'm going to go, that is not a new color. I wanted a new color. There we go. So here if we go up by c, I should make that more. Here I'm going to have my graph, which will look basically the same. We'll call it f of x plus c. And then here, if I shift it down by c, it follows the same curve, and it'll be f of x minus c. Actually swap this so I have black, not black. Okay, so we're doing this. So here I can sketch in my original function. So let's just say f of x equals x cubed. And so if I, not x cubed, x squared. So if I draw that in, 1, 2, 3, 4, 1, 2, 3, 4, you should be experts at doing this. Okay, so here I have that. My shifted graph, here would be, and I'll just, for the sake of argument, I'll just call it g of x equals x cubed minus 3. Or, I said minus, didn't draw it, minus 3. So I'm just going to move it down 1, 2, 3, and then I'm just going to mimic this graph exactly. And so the point of the transformations is not that you have to redraw everything, it's that you do it in such a way that you can just mimic the graph and do that. So here for the x cubed, we're going to move it up. So this means go up by 2. So actually, let me actually write what you probably put on your exam. So here, this would be f of x, or x squared, shifted down by 2, or by 3. And here, this would be x cubed shifted up by 3. And this is what you'll probably put in the exam. I'll just say it's shifted up or down by x amount. And this is 2, so here we're going to have f of x is equal to x cubed. So x cubed looks like this, if you remember from last time. Oops, that's the wrong spot. Here it is. And then here, oops, I lost my color. I lost my color. I don't know what I did. I'll have to figure that out. And then here, if I shift it up by 2, I just go here, draw the same spots, and then follow. Okay. This one's super, are we supposed to write out the answer like that? What I probably will do, what I'll probably do is you'll have a drop-down menu, it'll be up or down. by 2, or I'll just say, I'll edit the practice exam and put something on it to make sure it matches it exactly when I finish writing the exam today, okay? And I'll just write practice exam, and I'll write practice exam edited on it, okay? So that way you can see it. And I'll go over that problem tomorrow. Just remind me tomorrow to actually go over how we type it in, okay? All right, so this is vertical shifting, not horribly interesting. Any questions on that? Can we even graph on Canvas? No. The answer is no. So we're gonna have to do, this is the one section which is, it's the easiest section to understand, but it's probably the hardest for me to test you on just because we don't have graphing powers on Canvas. So if I had you guys buy the book, yeah, you could graph at the little thing, but yeah, it's basically, I'm just gonna say shift it up or down. I think there's a way to get little pull down menus, and then you can just have them pull down menus and then fill in a blank. That's what my hope is, right? I don't have to mess with it more because I'm still kind of new. All right, to writing in Canvas, I'm not used to writing in either my Pearson, or Pearson does what, my math lab, or whatever they changed it to. And then the other one does WebAssign. So I think you guys may have worked with those before, maybe. So let's do the next one. So horizontal shifts. All right, so this one is a little bit less counterintuitive than the other one. So let me just draw in some function here. Say this is f of x. This kind of more or less the same function. This is f of x. So now, when I change this, so f minus c is going to be moving to the right c unit. So when I minus c, I'm shifting it to the right. And so that's kind of slightly counterintuitive, because you think, well, if I'm minusing something, I should go in the negative direction in the x, but in actuality, when you do it this way, you actually go in the positive direction next, and I'll explain that in a second. Let me just do the other one real quick. So if I add c, I'm moving it to, oops, that does not match that greatly. There you go, that's a little better. And this is f of x plus c. And let me kind of explain it to you using, I'll actually use the live example to explain it to you. That'd be easier to do. All right, so let's go back to the black. So let's draw in our two standard graphs here. So we're going to draw in f, so we're going to draw in x. So here's my x squared, and here we'll go ahead and draw this one into, so the original graph. So here f of x, here the original would be x squared, here the original graph here would be x over 1 over x. You guys see where I'm getting what the original function is. You just get rid of, you just simplify it basically. And so here, that's what it looks like. So these are the original ones. You should be able to roughly graph these in your head at this point. So let's go to the alternate versions. And so here I'm going to take x squared and I'm going to shift it. I'm going to shift it to the right by 2. And here I'm going to shift it to the left by 2. So this is 1 over x shifted to the left by 2. And the reason is, let me actually write out g of x real quick. So g of x equals x minus 2 squared. So when I plug in g of 0, this is equal to negative 2 squared. And if I plug in g of 1, this is equal to negative 1 squared. If I plug in g of 0, or 2, this looks like 0 squared. And if I plug in g of 3, this ends up being 1 squared. And so when I minus 2 out, when g is 2, it looks like 0. So here, when I minus 2 away, I'm moving to the right because the graph has to, let's see how I can explain this. If you imagine, let me see if I can draw something really. I'll give me a whole new one. Give me a whole new sheet real quick. New sheet me. Because if I explain this correctly once, you'll get it forever and then you don't have to worry about it. So imagine your function currently is a little car, right? And it travels through the x-axis, right? And so here at 0, for the function of f of x equals x squared, actually, I should have probably done this in black. That's fine. I'll just switch to a different color. So here for f of x here at 0 for x squared, it's the value I get is 0. And here at 1, I get 1, and here at 2, I get 4. And so as this car kind of like moves along the track, I'm producing these numbers. Now, if I have a different function, let me just use this blue, I guess. So here if I have f of x equals x minus 2, it's kind of going to go through the same motions, except this car is going to pretend like it's 2 behind, right? So when this car, so in this function, back to purple real quick. So when this function's here, so when that function's here at 2, the same car would look like it's at 0. So this would be my g. Let me make this a g of x. So this looks like it's at 0 as it's traveling through, and so it's behind, and so that's why it moves to the right. And so here at 2, it looks like 0, and at 3, it looks like 1, and here at 4, it looks like 2. And so here, it's just always going to be slightly behind. And so that's what causes, if you can think about it that way, I'm going to go back to here, go back to my purple. Oops, one more. So when we go back to here, this really looks like 0 to this function, right? This 2 really looks like a 0, and this 3 really looks like a 1, right? And the 4 is really going to look like the 2. And so here, when I draw this, it's just going to be shifted to the right because it needs to be further along in the x-axis in order to produce the same values. And so the negative, even though intuitively you want to think it goes the other way, it actually needs to be further ahead in order to produce the same graph. And so that's where that comes from. Same song, same dance here. When we do the g of x is equal to x plus 2. Now it looks like my x is higher than it is, and so it's going faster than this one. So here, when it was at 0, so I'm just drawing my little asymptote, it looks like 0, and so this graph here, and this graph, oops, won't go through that. Won't go through that. Let me try it again. So here it's just shifted over 2 units, and so you can move it to the right. So that explains that. So basically just change the starting point where it's driving. Yeah, so that's basically it. Now you guys get the idea. So one thing, just be careful, vertical, from going from vertical to horizontal, it looks different, right? So if you do, it's always, you'll see it again. So for the horizontal, when you mess with X, it does exactly opposite of what you think it does, or your intuition tells you what to do until you retrain your intuition. Okay. All right, so let's do reflections. So here, if I plug in f of minus x, we reflect the graph across the x-axis, or negative f of x. Negative f of x is reflected across the x, or f of negative x is reflected across the y-axis. So I'm going to draw 2 different ones this time because it's easier to see with 2 different ways. All right, so here we're going to draw this. I'm going to call this my f of x. And then here I'm going to draw something that looks like if I'm going to call this my f of x. All right, so let's do each one slowly. So here I'm going to reflect across my x-axis, and so I'm going to plug in minus f of x, right? And so here, if it was negative, it becomes positive. If it was 0, it stays 0. And this looks like this. And so this would be minus f of x. Now, what I'm doing here is I'm reflecting across the y-axis. And so what happens is that we just kind of run the card backwards. And so I start here and go like this, because my positive values look like negative values and my negative values look like positive values. So basically I'm running the card backwards in this case. And so it gives you that. Okay. All right, so let's actually crunch through this. Go back to colors. And there are some serious advantages about doing some of these nets with the tablet, because I get infinite colors and I can just erase real easily. All right, so here, let's go ahead and draw in x squared. It's always x squared for the first one, and then I give you always something different for the second one. That is not x squared. X squared is here. I think if I'd drawn it all day, I'd be good at it. All right, so here I have x squared. So f of x is f x squared. Here our f of x will be just square root x. And so let's do our alternate versions. So here I'm going to, so minus f of x. So what is that? That is reflected across the x-axis, right? So this would be, oops, I don't need the minus sign there. So be reflected. How do you spell that? Reflected across the x-axis. And here I have it on the inside. So this is g of minus x squared. And then this will be g of minus x. So this is square root x reflected across the y-axis. Okay. Oops, I didn't draw in my x. Draw that in real quick. All right, so here, so I'm going to reflect this across the x-axis. So if I just drew, if I drew a little mirror here, this is the kind of like the fancy term for, and if you do physics or something, this is usually a reflective surface or mirror. That's what they use. You may see that in engineering. I don't know if they use the same symbols. I think they do, but I'm not positive. So you just flip it over the x-axis, and here we're going to reflect it across the y-axis. So here's my reflective mirror. So if you slap down a mirror here, notice here that positive values are not in the domain, but negative values are. So real quick, what's the domain? What's the domain of g of x? What's g of x's domain? See if someone can give me that answer real quick. Yeah, x less than 0. So here I can have x less than, it can equal 0 too. It's just hard to type that in. Yeah, perfect. So less than equal to 0, or from minus infinity to 0 inclusive. Remember, you can plug that in. All right, so these are the reflections. Let's do vertical shrinking and stretching. All right, so if we multiply by a factor of c on the outside, it's just going to it's just going to vertically stretch or shrink it depending on what the factor is. We make c strictly greater than 0 in this case, and the reason we do that is because if we make c negative, it's like a reflection and then a shrinking, and so you can just split it into 2. So here we can safely say this is 0. If c is 1, we've done nothing, so that's why I'm saying it's not 1. So this just stretches it and shrinks it. Let me see what. So let's go ahead and draw. Let's say this is my f of x. Let's go ahead and just draw another one of those. This is my f of x. Switch colors. All right, so let's say I'm stretching it by c. So I'm just going to. So it should just be c f of x. And here I'll have c greater than 1. And here if I have c less than 1, it just shrinks. Notice it still should go through the zeros at the same point. It just kind of squishes it or shrinks it. And this is c f of x, where c is between 0 and 1. So it kind of just stomps down the function. You guys ever seen Yellow Submarine where the blue meanies go around stomping butterflies? That's what I think of. If you haven't seen it, don't worry about it. It's a very old show. Actually, it's an old movie from the Beatles. I grew up, I was in Portland for 10 years. We learned all the hipster rules. And being liking the hipster is part of those rules for some reason. So let's just do this real quick. So let's have our x. Oops. Our x squared. So this is f of x squared, and then we're going to have our function here will be f of x equals the absolute value of x. I don't know if we graphed this one last time. So 0 causes the stretch. So 1 causes this. You can't use 0 because, let's see how I can say this. If I plug in 0 here, so f of 0. So hold on. All right, let me make this very, very clear. Y equals 0 f of x. No matter what f of x is, y is equal to 0, and then you have infinite shrinking of a line. So if it's 0, it is a line at y equals 0, because nothing that you input here will change that except for very certain rules, but you won't deal with that. I meant, so the zeros, oh yeah, so the zeros should still end up at the same point, because 0 times 10 would still be 0, right? Or 0 times 1/10 is still 0. And so yeah, the zeros, it should cross the x-axis at the same point. So this should be the same. This should be the same if I drew it correctly. Thank you for clarifying that. All right, here we can draw this in real quick. Oops, I didn't want to do that. Boop, boop. There we go. So the absolute value of x looks like this v. I don't think we did this last time. So let's go ahead and do this. And so here we have, this is stretched. This is vertically stretched. Stretch, STR, stretch by 3. And this is vertically shrunk by 0.5. So let's go ahead and draw that. So here, notice when I have 1, so at 1, 0 is still going to be 0, so that's still the same point. At 1, it's going to be up by 3, and at 4, it's already at 12, so it's just like, so it's just way more narrow, right? So I've basically taken things stretched way tall. Here, I'm going to shrink it by 0.5. And so here at 1, it's actually only going to be a half, and here at 2, it's only going to be, so it's still 0 at 0, but here it'll be at a half and all the way up to the 4th. And so let me just draw that in. Oops, I didn't finish it. Be that way. And so here I vertically shrank it or squished it down by half or by a factor of 2. Depends on how you want to say it. All right, let's do horizontal stretching and shrinking, then we'll put it all together. All right, so here, so like I said, when you put it inside the function, when you mess with x, it's so the larger C actually squishes it faster, and the smaller C actually stretches it faster. And I'll explain that again, probably with the car analogy again. So let's go ahead and do this. So let's just draw in the same more or less things and kind of explain it this way. All right, so here I'll have my f of x. This will be my f of x. All right, so I'll swap this out. All right, so I'm going to stretch it by c. That means c is between 0 and 1. And so here, let's see if I can draw this very, very carefully. So at 0 it's still going to be the same point because c of 0 is still 0. So at this point still, but it's going to be it's going to just take me longer to perform the same sort of thing. Okay, so here it's just going to stretch it out this way. And here, if I shrink it by c, it's also going to start at the same point, but this time it's just going to go through it. And this will be f of, this is f of c of x, and this is f of c of x. And this is between, or this is where, this is where c is greater than 1. And so if you think about this, so let's pretend, let me go back to my car analogy real quick. Hi. Oops, not what I wanted. Sorry, I told you it was not what I wanted. Perfect. Right. So, oops. Fine. Do it like if I was painting. So let's pretend we have two cars real quick. So we have our function c of f of it's not c of f of x this time, it's f of c of x. And then we have our other car here of f of x. And just for fun, let's pretend they're on the exact same highway and it goes up and down and all this other stuff, right? Right? And they're both driving the exact same road. So the exact same function. Depending on what C we put in here, right? Oops. Nope, I did not want that. Go back to my pencil. So depending on what C we put in here is how fast this car travels. And so if I put a really powerful engine in this thing, say I put a little rocket pack, like pretend we're on like Looney Tunes, right? This thing's going to crunch through the function way faster, and therefore let's go back to this. And so if I put a real powerful engine in it, say this is the normal speed of the track, if I put a powerful engine, it's going to fly through it really fast. And if I put a really slow engine or give it a large weight, it's going to slowly go through the same motions. And so it's the opposite of what you think it is, because it's how fast, I think of it's the engine, how fast are you crunching through your function. Because I'll show you here with actual numbers to make life easier. So let's go back to numbers. Let's go ahead and draw in our f of x. All right, so this is my f of x. It's equal to x squared. Here, I'll have my f of x here is equal to x. Swap this over. All right, so now for my little g of x here, which I'm going to do in purple, of 0.5x squared. Notice when g of 2, well, g of 2 looks like 1, right? And g of 4 looks like 2. And so here I'm stretching it horizontally because it just takes me longer. It just takes me longer time to go through my function. And so here, this will be at 2, it looks like 1, and here it looks like 4. And so here it looks something like this. That's really kind of wobbly. I probably should put on my glove. My hand's getting sticky. So it just takes longer to go through the function. And here, I can do my f of x here, 4, go through here, go through that. All right, and then here. But now I'm going faster through my function because here g of x of 3x, so g of 1 looks like 3, or the square root of 3, g of 3 looks like the square root of 9, and so it's going to be much higher. So square root of 3 would be about here. Let's see, a 3 I'm at 9. So that'd be 3 even. And so then I look like this. And so this is actually squishing that graph in. The difference between vertical stretching, you can translate vertical stretching and shrinking to horizontal stretching and shrinking if you're good about it for these functions. So they kind of look the same a little bit. So these are just things we just get used to. And so let's kind of put it all together. And then we'll talk about even and odd, and then we'll go from there. You'll have a couple. I'm probably only going to give you one exam question, and I'll probably make it real obvious what to do for this one. And then I'll give you a sample one that's close to it, just because I don't want you to get too confused, but this is important. Messing with graphs become very, very important for calculus, and so that's why I still wanted to go over this. All right, so here, what's my original function? Let's see if you guys can give me that. What's my original function here? If I was going to say f of just boring f of x, what is that? Yeah, x squared. It's always been x squared for the first one. All right, so here, but what am I doing to this one? What am I doing to this one? What are all the operations I'm doing to this one? See if you can label them all out for me, and then I'll do the other one. So what am I doing to this? So I'm going to shift it up by 2, so that's correct. So we're going to shift it up by 2. So shifted up by 2. It is an x. So we're going to reflect it across the x-axis. So I'm going to put reflect across x-axis. And then I move it right by 1. Okay. All right, so here, basically I'm taking my center point that used to be here, and I'm gonna move it over to, I'm gonna move it up to 1, 2, and over 1, so here it is. And then I'm gonna flip the whole thing upside down, and so it looks like this, where my original looked like this. Okay, and so here I moved it up to over 1, and then I flipped it over the x-axis. Okay, there's an order to these. I'm not going to make you worry too much about them. Just double check it. So I think you shift your point and then you do the reflections. So here, this one's a little bit harder. I give you one on the homework, so I'll let you guys, I'll crunch through this one for you. So this one, I'm going to simplify to be 2 of x plus 1 minus 1. And the reason I do that, because this makes it easier for me to see what I've done. What have I done here? Now notice this 2 can be in or out, it doesn't matter. That 2 can freely move, and so it ends up being the same. So here, my new point here, so my new center in my mind, so I moved it over by 1 and 1, right? So I moved it to the, so I'm moving it to the left by 1, and I'm moving it down by 1. So my new center point, so if I started here, draw this in while I still have my black. Oops, hi, there. And so if I started here, I'm going to move it down 1 and over 1. Okay. And notice I'm stretching it by, or either shrinking it by 2 or stretching it by 2. In this case, it ends up being the same. So it goes to here, and then to here, and then to here, and then to here. And so I tap, and then yes, yes, yes. Oops. Tap, hold on. Here, here, And so that's what we've done to it. All right, so yeah, wouldn't so stretch by 2. Yeah, wouldn't it be in the original? I guess I missed your question, Gabrielle. Could you restate it for me, I guess? Oh, so be left by 2. So here's your question. Here's your question. So I see what you guys are saying. So why is this not left by 2? And why is it only 1, not by 2? And so this is an important thing. That's why I give this as an example. Here I have 2x plus 2. This, so here, let me see if I can be very, 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 very clear. I think I want my extra paper for a second. All right, so here, let's look at this. So here I have 2x plus 2. We'll leave the other part out for now, okay? So here my f of x, my original f of x is the square root of, as the absolute value of x, okay? Everyone by that's the original, or at least the original function that we're messing with. Notice here, if I have f of x of 2x, I've done horizontal shrinking by 2. Here, or rewrite that. Not what I wanted. Definitely not what I wanted. Back to my pencil. So if g of x, I move it by 2, and then let's just say h of x, I move it over by 1. Okay. So here I'm doing this transformation, shrinks it by 2, this moves over by 1. So, but why it's, I don't know, let's just call this q of x. So why is this not 2x plus 2? And so the reason is if we go way, 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 way back to this one, notice I'm plugging in c of x for everywhere I see an x. And so let's go back to this. There we go. So so here, hold on. See, I can explain this correctly. I see what your question is. Why does this matter over that one? Let's see if I can explain it without get you guys lost. I think it just goes into, I think you kind of run order of operation backwards is the best way to explain it. So addition needs to happen. So you need to factor down to addition first. Let me make sure I'm not losing my mind real quick. I have before in the past. Let me make sure I'm not lying to you. Never let your teacher lie to you. Because sometimes they're like, oh, I know everything. They say that, they're lying. Liars. Let's just graph this real quick. Let's make sure I'm doing it. I am doing it correctly before I. So ABS. So ABS is what you use to do absolute value. So it'd be 2x plus 2 minus 1 is what we had. Yeah. Okay, so I am doing this correctly. So it is, so here it is at 2 minus 2 minus 1. The reason is that in order of what you put stuff in, it's backwards. And to get into why that is might get us both lost. So the reason, so let me just write something real quick. So the order of these things is, so the order which you do stuff is vertical / horizontal shift. So that's the order. And then you do, the reflections. And then it goes the shrinking. or the stretching or shrinking. Stretch. So this is the order in which you perform these operations. Would you get the same graph with either results though? The answer is no, because if I did two, let's go back to this. If I move this down, if I move this to the right 2, I'd be here. And then then there would be no reason for the absolute value to go down. So you need to be very careful when you do this. And so when you perform the operations, you're going to do the vertical, horizontal first. And in order to do that first, you have to factor it out. Okay, so the orders of these notes isn't just for kicks or just of these. It's actually the order in which you perform the transformations. Okay, so the order which the notes is very particular. So it's better just to factor everything. Yeah, that's the best way of putting it. Okay. You'll have something like this. You can always check it right now. Currently, since we're all remote, you all have a calculator, so please check your answers. Or check it in Wolfram Alpha. I show you how to type it in. So you do the order of operations. You do it in the order which they're presented. So you move it, you shift it first. Notice here we shift this first and then flip it. Like I said, this one doesn't matter, but this one does. So, all right. Any other questions on that? You'll have some homework and we'll have time to go over it more tomorrow. Nope. Okay, so let's finish this up and then we have about, what, a half hour to do the other one? Yeah, so let's just finish this up so we have plenty of time for the next one. All right, so if F is, so here we're talking about even and odd functions. So let's just crunch through this. So a function is called even or odd for a very particular reason. I'll just give you the answer now just because you're short on time. So the reason we call it even or odd, so if you look at your polynomial, let me do some, then it'll be easier to explain. So an even function, so basically to tell if it's even or odd, you plug in negative x, and if you get the same function back, it's even. If you get the negation of that function, it's odd. Most functions are neither. So most functions are neither even or odd. So you hear even, I think one or the other. In the case of functions, most of them are not. So here, let's just crunch through one. So here, f of minus x is equal to minus x plus 3, which is equal to minus x plus 3. So this is neither the same function, nor is it the negation of this function. So this one's really neither. So this one's neither. Let me do one that actually turns out to be interesting first. Let's just go to B. So here, if I plug in minus f of x into this, I'm going to get 4 times cubed plus 2 minus x, minus x. And so this gives us minus 4x cubed minus 2x. And so this is actually the negation of this function. So this one is odd. And here, if we do this one, f of minus x, here I get x minus x squared plus 4 equals 3x squared plus 4. And so this is the same function, so this is even. And here we can see what's going on here. So technically this is x to the 0 power. This is x to the 0 power. And so if I have all my polynomials, this is x to the first. So if all these are odd, I'm going to get back the negation of the function, so that which makes it odd, right? If all these are even, I'm going to get back the negation of, I'm going to get back the same function I had, which is, so therefore it's putting in negative x is going to give me back the same function, so I'll get even. If I have a mixture, so this is 1 and 0, so this is a mixture, so this is neither. You will see this again here, that f of minus x, notice this is a mixture because I have 1 and x of 0 technically. X to 0 power is 1. So this is giving me 2 minus x squared plus 3 minus x plus 4, which gives me 2x squared minus 3x plus 4. So this again is neither. So most functions end up being neither. How about E? Is this even or is this odd? it's even. And so in this case, it's even because if I plug in, hold on, minus f of x, minus s of x here, well, I plug everywhere I see an x, it's still going to give me just 7, which is the same function, so it's even. And what is this one? If I plug in minus f into this, so this one's also even because this is just the same as f of x because it doesn't matter. And so I gave you, on the homework, I gave you one function, which is EvenOdd, which gets you close to that. You may have to look it up, but that's fine. So this just is a way of saying a function's EvenOdd. These will probably be multiple choice, so just say, tell me if this function's EvenOdd or neither, and just click on it. On the homework, do you have to show your homework like this, or can we use mental math? You can use mental math. Try to show, at least if you have to scribble something down, try to write it on the paper, right? But for stuff like this, you can just instantly say EvenOdd and all this other stuff. And one of them, I give you cosine of x. You'll have to look that one up probably, why that's even or odd. And another way of telling an even or odd function is if you can flip it across. So what does this do? What is this right here? What's this? Let's go back to my reflections real quick. Reflections, yeah. So basically, if I flip it across the y-axis and it's the same graph, that makes it even. Okay, so if I can flip it across the y-axis, the same graph, that makes it even. And so you can just kind of go, you can use that one to show why sine or cosine is even or odd. Okay. All right, so that's the end of these notes.